Good morning, folks. So I'm just going to have kind of a review lecture. Some of you have already been going through these slides, and that's good. They're pretty self-explanatory for taking notes. This is more of a background. I suspect many of you have already heard of the states of matter. Not these states, of course. States that matter. No, I'm just kidding. But physical states of matter. So I want to run through these, and I don't want to spend too much time here. Hear my voice droning on. But four states of matter. The ones most important to us are solid, liquid, and gas. Okay, plasma is this state was kind of discovered or described earlier in the 1900s. We've known about it a while. It's briefly here on Earth in space, such as our sun. It's not brief, but briefly present matter particles that are highly charged, ionized matter. So you're talking about a lot of negative charges all in one place, or a lot of positive charges all in one place. Anytime you have those types of environments, that's like lightning, that's fire, that's electricity. So it's matter and particles, and easiest way to think of them is in a gaseous state, but in a gaseous state that is very condensed. So again, like our flaming ball of light in the sky, the sun, that's a plasma. It's a lot of ionized particles, but it's confined. Typically, a gas is defined, unless you have it in a container, it's very random and it's only contained because of the container. Well, plasma is somewhat contained, but without a container, right? So fire, lightning, the sun. There's nothing surrounding lightning or fire or the sun, but yet it's in a circle, right? The sun under gravity and such. You might remember from earth science. Lightning, of course, is very irregular. Bolts, nothing containing that. But then it's gone in a flash. Fire, you see the flames whip out. All right? So nothing containing it. So those bright light moments, heat. There is cold plasma, but bottom line is it's not what we come into contact with every day. Solid, liquid, and gas are what we come in contact with every day. We'll spend most of the time describing that, okay? So what defines the state of matter? The particle arrangement. When we talk about particles, it's usually molecules or atoms, compounds, things that are mixed. And so those particles can be arranged in various number of ways. Really tight and barely moving, that's a solid. Okay, if the energy of those particles, they're arranged in such a way that they're not tight together but loosely held in one spot, slowly moving, that's might be a liquid. And liquid has more energy. And then of course, arrangement, if it's scattered and everywhere, that's the description of a gas. Okay, so that's what we mean by particle arrangement. And that particle arrangement is influenced by the energy of the particles. So when we say energy here, we're not talking only about electricity, only about heat, we're talking about kind of just, and this is very difficult to imagine maybe, but it's just the inherent energy of it. And next slide, I'm going to describe that kinetic theory. So you might recall from either physical systems or other that there are two kinds of energy, kinetic and potential. Potential energy is not really doing anything, but it has the potential to do something, like the rock at the top of a hill. Whereas kinetic energy was the energy of motion. Any object in motion is displaying an amount of kinetic energy. So if you look up the word kinet or kinesis, like kinesiology is the study of movement. That's what PE majors do in college. They study kinesiology. That word kinesis is move. So the study of movement. So kinetic, ik means pertains to, the IC, kinesis, once again, is to move. So it pertains to moving. So where does the energy come from? Again, we say it's inherent. Back in the 1700s, a guy named Brown, scientist by Austin Brown, described it, and it's been named after him. It's called Brownian motion. So Brownian motion is the random motion of any particles. If you've ever seen a sun ray come through your window or in your car and you see all the dust going everywhere, it's just random movement due to the air flow, possibly the weight and size of that thing. It looks really random, and that motion was described as Brownian motion because of Brown. And there's nothing adding energy to it, nothing pushing on it, no electricity in it, no fire. It's just the energy present within the system itself. And that influences the arrangement, which is the distance between particles. So this idea is called the kinetic theory of matter. All matter is in one of those three states. It's either a solid, a liquid, or a gas. And matter is made up of particles which are in continual random motion. So solids are arranged very tight and close together. They vibrate in place. They're trying to move because of their energy, but they just don't have enough movement or force to break those bonds. So they're in a fixed position. They have a definite shape and a definite volume. Now, if we add heat to that, that's energy being added to the system. That's going to cause bonds to break and molecules to move faster, just like you would move much faster the hotter it gets. Touch a stove or an iron and yo, right? That's a very quick response to heat. So once we add heat, we can convert that solid into a liquid. Now it's a little more fluid. This is what you call a melting point, right? So particles of liquids are tightly packed but are not far enough apart to slide over each other. Okay, but they're not just vibrating in place either. So they have an indefinite shape. They take on the shape of the container that holds it, right? If it's a bowl, it's round. If it's a cylinder, it's a cylinder. It's straight up. And they have an indefinite shape and a definite volume. So it's measurable. So whatever container is holding it, we can weigh it. We can measure it by volume, cubic centimeters, or liters, milliliters, whatever that volume is. We can measure a volume. It's hard to measure the volume of a gas. It does have a volume. Solids have a volume, and they have a definite shape. Liquids have an indefinite shape, but they do have a definite volume. What if we added more heat to this? What would happen to the liquid? Not only would it melt, but it hit the vapor point, or heat point of vaporization, and then it becomes a gas. All right, so more energy to the gas. All right, particles of gases are very far apart and move freely. As a matter of fact, you don't see any in here. Gases have an indefinite shape and an indefinite volume. That is, it's very difficult to measure the volume of air in this room, right? We'd have to seal it off. Nonetheless, we can. The acetyl tanks you've seen for welding, possibly oxygen or hydrogen tanks. You've seen for those who have oxygen, we can put it and we measure it in pounds of pressure. Pounds of pressure. The volume is going to fill whatever you put it in. What's different is how many pounds of pressure that it has. So you still can't really measure the volume of a gas even in a tank, but you can measure the quantity based on pounds of pressure. That's what they call it. And so it's an indefinite volume. It's going to fill whatever space it has. And what if you added more heat to gas? Well, you get very hot gas. And more random movement of the molecules. So now we're interested in phase changes between those. So you already got a hint that each time we added heat, we were able to change the state of that matter for whatever it is. And every substance has its own melting point, its own freezing point. So let's take gas, for instance, and let's go backwards. Here we had been adding heat, but what if we removed heat? Well, those molecules slow down. If we remove more heat, they slow down more and they condense. So this is condensation, and they become a liquid. That's what happens to air when warm air hits, say, the cold windows of a gas station, or when the air surrounding your cold can of soda, it begins to move so slow that it actually condenses into a liquid and then sticks to the outside of that either window at the gas station or the surface of your soda. So particles of liquid are so we removed heat, and we have liquid. If we remove even more heat, then the particles really slow down, and they may, if enough heat is removed to become a solid. All right. So adding and removing heat is how we change the stages of matter. So these phase changes, solid to a liquid is called melting, liquid to a solid is called freezing, and the heat goes into it, melts the solid, heat leaves it, freezes. Liquid to gas is called vaporization, which includes boiling or evaporation. As molecules escape the system, the liquid becomes gas. You've seen this on a stovetop, and the heat goes into a liquid. As it vaporizes, it becomes a vapor droplets in the atmosphere. Gas to liquid is condensation. Heat leaves the gas as it condenses. And then solid to gas is called sublimation. We'll notice on this last one that we actually skipped, right? We skipped to the liquid portion. We went straight from solid to gas. That's what you call sublimation. Heat goes into the solid as it sublimates. And you see this possibly with dry ice, liquid nitrogen, just very quickly. But what happens if you raise the temperature and add so much to super high levels between, say, 1,000 and 1 million or 1 billion degrees Celsius? Will that gas ever be contained? Can you break the forces of those atoms? Well, you're looking at it, right? This is fire. Those are brief moments, very intense heat. It gives off a lot of light. There's no more heat, actually. There is heat given off from the light, but that light is pure energy, practically. And we get to states of matter, such as plasma. So plasma is the common state of this kind of ionized matter. It's an ionized gas. Ionized means it has a charge, and we're going to learn more in this class in a few weeks what it is to be an ion. But for now, I'll just tell you that an ion is a positive or a negative charged particle. Not both. It's either positive or negative. It can be a negative ion or it can be a positive ion. Ion just means charged particle. So plasma is an ionized gas, and that's what happens in the atmosphere with lightning. You have a whole bunch of negativity up in the clouds and positive ground, and you have a lightning where lightning coming from the sky meets lightning coming up from the ground. Or cloud to cloud, where you have a negatively charged pocket and a positively charged pocket, and you see lightning shoot from one cloud to the other. And that's not striking lightning, it's going across the sky. And these are due to ionized gases. So plasma is a very good conductor of electricity because of that, and is affected by magnetic fields. So if we can control magnetic fields with those ions, we have cold plasmas, such as on your plasma TV. So there's two particular kinds of elements that are involved in that one. All right, so here's a graph that you should, you'll see it in a number of different ways, and it goes from solids to plasmas. And you'll notice this plus E. What do you think that means? Right, energy. So each addition of energy creates a change in state. And here we're seeing the solid, liquid, gas, plasma. Okay, know these descriptions. Recognize the descriptions both verbally and in picture form. Okay, that will be on the test or the quiz. So there's just some finishing up slides. I've already talked about this. Fire, lightning. I haven't said this one, but that's true. Aurora borealis, the northern lights. Ionized way up there due to magnetic fields. Biggest state of plasma in our solar system. All right. Okay, so I think and hope that was short enough as a review of states of matter. I'll get on to review. So today, I guess while I have you on here, I will show you. So you'll go through those, and you have this doc here that you'll open up, and plenty of things to read and look at. And you do want to, because there's more to it than what I talked about. This was a review video. It took me about 14 minutes. But here, click on Chem for Kids, read. You can see what your student will be able to identify, blah, blah, blah. So you should be able to do these things by the end of the lesson. And there's a lot more here. This goes into tomorrow's lesson as well. So physical properties is what we want to review. States of matter you can review by reading. Here's a nice diagram. Okay, that tells you the process of going, say, from liquid to gas is evaporation. Going from a gas to solid is deposition. You're depositing. It's like condensation. Gas to liquid is condensation. Sorry, gas to solid is deposition. See? Diagram's already working. Sublimation, going from solid to gas. So kind of study that. Read through slowly. You don't have to answer all the questions on all the readings. You don't. I would probably write down a summary statement or three after each reading. If you can read the questions at the end and answer them in your head, you're fine. If there's new information there, I would probably write it down. Review kinetic molecular theory is here. A lot of these have videos that go along with them that are good to watch. So this could easily be the complete lesson for your notes and questions right here. All right. Okay, so that's day 3, properties of matter, review of the states and what causes phase changes. And here's the readings. As you do this, remember, you can make a copy of this for yourself and you can write on this. You simply go up here to File. You can't see this, but make a copy. And when you make a copy, again, they'll say copy of properties of matter. You can put your name on it, title week 1 notes. And if you begin to do this, with each lesson, you'll have your notes. You'll have your notes in document form. Of course, you're welcome and able to as well just write this in your paper notes. Okay. A little later, I will put up a small. It'll either be a Flipgrid short video clip or it'll be a Google form quiz, like 2 questions. Won't be much, and you'll want to do that by midnight tonight. Okay, to be accounted for. So get some of this done. Look through it, and it'll prepare you for both the post or the Google Forms, whichever I pop up there this afternoon, and we're done. All right. If you have any questions, let me know. I want to throw a quick shout out. Remember, at the end of the day, I open up my personal link. I've emailed you guys. I'll send a reminder of what that is if you need a reminder. And you can talk to me and we can interact face to face right here, just like I'm talking to you here. And you don't have to show your face. You can turn your camera off. I can still hear your voice. All right. Have a great Wednesday. Hump day.